One comment I wanted to make is that I mentioned, I think last time, that I'm currently giving a mini course on NSOP1 theories, which is something we'll get to in this class, at Fudan University in Shanghai. And I'm giving them very early in the morning. It would be 5 a.m. California time. But they're evidently being recorded. And so if there are people interested in following those or like checking them out, then I will post them on the course website once they're available. I think Daoud and Iran are like the heroes that are going to both. I couldn't imagine listening to me for 3.5 hours in a given day, but some people are trying. Okay, so that's just a comment. So be on the lookout in case you're interested in more, because it's relevant to the class material. Now, what did we do last time? Last time we proved that if you know that you have a class with the Ramsey property, then that implies that you can find indiscernibles indexed by infinite structures whose age is that Ramsey class. Now, that just means that we get a whole bunch of indiscernible structures for free because combinatorialists have been doing the hard work for us. You know, like there are people in combinatorics that prove that certain classes are Ramsey, and now we just can cite those theorems to get indiscernibles. So they have done the work for us, and we get to reap the rewards. So I'm going to share my screen now, and we'll start focusing on a particular example of an indiscernible structure. The STR indiscernible trees. And this is going to be one of 3 kinds of indiscernible trees that we consider. And we're going to start and hopefully finish proving this theorem of Shelah, that you have the tree property of the first kind if and only if you have, or sorry, you have the tree property if and only if you have the tree property of the first kind and the tree property of the second kind. Okay, so let's start with tree indiscernibles. Okay, so let me switch this. All right, so tree indiscernibles are what, I don't know, it's sort of like the bread and butter of model theoretic tree properties, because if you want to prove something, it's just somewhat too complicated to prove it for the whole tree at once. And when you have a tree indiscernible, then you can somehow focus on a single path instead of looking at all the paths. So you can focus on a single pair of vertices instead of looking at all pairs of vertices. Now, the language that we're going to look at, the L prime, the index model language, is going to be the following language called STR, LSTR. And this consists of the following symbols. So you have this, which is the tree partial order. You have the lexicographic order, less than sub lex. You have the length partial order. And then you have the meet function. Okay, so you can look at omega to the less than omega as an LSTR structure. Or 2 to the less than omega, or kappa to the less than lambda, and so on and so forth. I mean, there are lots of trees that you can look at, but omega to less than omega is going to be the one that we care about now. So how do you do it? Well, the tree partial order, I mean, you can think about elements of omega to the omega as finite strings of natural numbers, and the tree partial order is extension of strings. The lexicographic order says that if 2 things disagree, then you look at the first place where they disagree, and then after that point, you see where they go. So, you know, if they branch, and then the, you know, eta goes in the, I don't know, in the k direction, and nu goes in the k plus 17 direction, then nu is lexicographically greater. Okay, then the length is also clear because every element of omega to the less than omega is in omega to the n for some n. So if you have eta, which is in omega to the n, and nu, which is in omega to the m, then if n is less than m, then eta is less than sublength nu. something like that. So this just compares the length of strings. And then the meet, you look, if you have two things which are incomparable, then the meet is the greatest initial segment, which is common to both, with respect to the partial order. And if two things are comparable, then one is an initial segment of the other, and then the meet is just the one that's the initial segment. Okay, so this conforms with what you know about trees. It's not super complicated. And there's a theorem which is called the Halpern-Laukli theorem. This isn't exactly what they proved, but it's it's a consequence of what they proved, which is that if you look at the age in the language LSTR of omega to the less than omega, this is a Ramsey class. So I actually think that Halpern and Laukli were trying to prove that the Boolean prime ideal theorem is not equivalent to the axiom of choice. I mean, it's actually like a hardcore set theory thing. It wasn't really a combinatorics. And then they had to prove some theorem about trees to prove that their forcing did what they said it did. But since there were also combinatorials that have established this theorem. But okay, this just means that LSTR indiscernibles do what we want them to, so we can work with them. Now, I'm going to define a kind of technical thing, but before we get there, maybe let's just think about a picture. So let's draw a picture like this. So here we have our tree. Now, first observation, if I take this path and I take
Nick, it's nothing showing up on your.
Oh no, did it stop? Okay, it's definitely showing up on mine. I'm gonna stop share and then restart. Okay, hopefully we're good now. So okay, so I've highlighted this path. Now, consider the tuples indexed by this path. So let's say this path here is called eta, and I'm looking at the type of things. So let's suppose that I have eta in omega to the less than omega, which is STR indiscernible, i.e. Omega to the less than omega indexed indiscernible, where omega to the less than omega is understood to be an LSTR structure. So these we will always refer to as STR indiscernibles. So before we called these I indexed indiscernibles, and what is our I? It's omega to the less than omega as an LSTR structure. So because indiscernible trees are almost always indexed by either 2 to the less than omega or omega to the less than omega. So the interesting distinction between them is not what the structure is, it's rather what the language is. So we highlight the STR part. So we'll call these STR indiscernibles. Now, I took this path. Suppose I take this other path. One thing to notice is, let's call this one new. If I look at the type of this path, so I look at A eta up to I for I less than omega in the language L, that's the same as the type of A new I less than omega. If I take two paths, then, okay, what does the type of this path say? Well, if you look at the indices, what do the indices say? They say, if I take this guy and this guy and this guy and this guy, what it says is that this is lexicographically less than this, which lexicographically less than this, which is lexicographically less than this. It says this is smaller in the tree partial order than this. This is smaller in the tree partial order than this. This is smaller in the tree partial order than this. It says this is less than in length this. This is less than in length this. This is less than in length this. And then it says that the meet of these two is the smallest one. The meet of these two is the smallest one. The meet of these two is the smallest one. So you know exactly what the answer is to every quantifier-free formula. You know how all the quantifier-free formulas are defined on this path. And that's going to be the same when you switch from one path to another. So these have to have the same type by indiscernibility. You'll also see that if I take like this sequence here, then this, so let's consider this blob. So these are all the things that are either less than or incomparable to this collection of blue things that I've written. So I've got this blob here, this sequence, which are the children of this node. And I look at all of the things which are in this blob, consisting of the things that are either less than or incomparable to the elements in this sequence. So I'm talking about this sequence here, the children of this node here. Notice that that's an indiscernible sequence over this blob, right? Because if I take something here and something here, it's going to sit in the same lexicographic order with respect to all of the stuff. It's going to sit in the same place with respect to the tree partial order, and it's going to sit in the same place with respect to length. So this is an indiscernible sequence going this way over the rest of the tree. Okay, and then there are lots more things that you can say about what indiscernibility means when it's on a tree. But sitting inside, you have lots of indiscernible sequences, and you have lots of things with the same type. Notice also that the path itself is an indiscernible sequence, because the language only talks about length. So if you take a path, if you take an increasing in tuple from the path, and you shift it up, it's also going to be in the same type because the quantifier free type hasn't changed. So there are lots of things that you can check. There are many things that are indiscernible sitting inside. You have many indiscernible sequences, indiscernible arrays, indiscernible trees sitting inside. So what I want to do now is talk about a particular indiscernible operation that you can do. So you start with an indiscernible tree, you get another one, and this is going to be called elongation. So this is going to be a little technical looking, but then I'll draw a picture and then it'll become clear. So suppose eta is in omega to the less than omega, then given k less than omega, we will define eta tilde in omega to the less than omega of length. Okay, so you look at the length of eta minus 1, you multiply by k, and then you add 1. I'm sorry for this. By eta tilde of I is going to be equal to eta of I divided by k, if k divides I and 0 otherwise. Okay, so let's take a look at, well, okay, sorry, and then there's one more thing, which is that we define the k-fold elongation of A eta in omega to less than omega to B eta in omega to less than omega, where B eta is equal to A eta tilde concatenated with 0, all the way up to A eta tilde concatenated with 0 to the k minus 1. Okay, so this is like a crazy definition. Let's see what it looks like, because the idea is going to be super simple, and you'll be like, oh, I see. Okay, so let's ask a really simple question. So if I start with the empty node, what does that go to? So what is the empty node tilde? Well, the length of the empty node is 0. It's the string of length 0. So Oh, wait, did I write this right? Because if I write -1, I think this -1 is wrong. Okay, but I should have checked this. It's definitely written this way in the paper which I wrote, so I should have done a better job. Okay, so let's see if this is right. So we want, no, sorry, I think it's the other way. I think it's +1 -1. Let's see if this is right. So okay, if we start with the empty node, then what does that go to? It should go to something of length k-1, where everything
Nick, are you
yeah,
writing?
I'm well, okay, can you see that?
Okay.
Okay, good. Okay, so all I did was I changed the numbers up here. So now it's length of eta +1 and then -1. I think I got the minus and the plus mixed. So okay, so what does eta tilde look like? Or sorry, empty set tilde looks like 0 through 0 to the k-1. Does everyone see that? So I mean, if this is correct, then length of eta is 0. So I have 1 plus k minus 1. So I should get something of -1 of length k-1. K doesn't divide anything between 0 and k-1. So okay, what do I get? I get all zeros. So it looks like a bunch of zeros of length k. And then what happens when I look at 0? So 0 tilde is what? That's going to have length 2k-1, and it's going to be all zeros. But what about 1 tilde? That's going to look like 0, 0 squared, dot, 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 all the way up to 0k-1, followed by 1, because k divides k. So at the kth spot, it should output what I get when I plug in k divided by k, which is 1. So oh, I see the issue. I think the issue is that this should be -1. Okay, now I think it's good. Because I want the first place, which is what happens when I plug in 0 to be this. Sorry about that. It's definitely written this way in the paper, which is not good. And then followed by a bunch of zeros up to k-1. Okay, so then what does this look like? I have a bunch of zeros, and then I branch off and go to 1, and then I have a whole bunch more zeros. And so the picture here is I somehow only branch at levels divisible by k. So this is like 3k. So I only branch at levels divisible by k. And every node at other levels consists of an extension just by zeros. And the elements in B eta will be like these length k blocks, like this. Okay. So the idea is if I start with a tree, then sitting inside of it, I have this tree sitting around. So I could take like this blob and this blob and this blob. And here I'm like at level 2. So I branch here. So, or sorry, here. So I guess I did 3. So 1, 2, 3. So then here I branch also. So, well, no, I branched here, sorry. So like here I could, well, I don't have a big enough tree to show you. But anyway, like this is like 3. So I branch here. So this would be like the 3-fold elongation. So the point is that I look at only the subtree of the places where I branch at things divisible by k. And then the other elements of the tree are just going to be extension by 0. So I just look at the subtree where I have 0 at everything except the places divisible by k. That's the only place I'm allowed to branch. And the point is, if I start with a tree, which is, so fact, if eta in omega to the less than omega is str indiscernible, then for any k less than omega, the k-fold elongation b eta in omega to less than omega of a eta in omega to less than omega is also str indiscernible. So the point is, I start with my tree and I look at just these blocks that I get of replacing each element, each sequence in my original tree with a tuple of length k, consisting of k things that extend the first node by zeros. So this is sitting somehow inside my old tree, and I've replaced each node. So this is like, this block now becomes like the empty node. This is like b eta. And then this becomes like b0. And this one like b1. And this block becomes like b00. And this block becomes b01, and so on and so forth. So I'm replacing each node with this like k tuple of nodes, all of which lie along a path and have length k, and I'm extending them by 0. Is the picture clear? I think it's like kind of confusing when you write it explicitly. Now, it should be very believable that this preserves STR indiscernibility, because notice, if I replace things by these blocks, I haven't changed the relation of, say, being in the tree partial order, right? Like clearly, if I have like the empty set is a initial segment of, I don't know, let's say 1, and that happens if and only if 0 to the I also know that like 0 to the k minus 1 is an initial segment of like 0 to the k minus 1 concatenated with 1. So it's very easy to see that like blowing up these tuples this way doesn't change the tree partial order. However, to prove it formally, you have to prove that must prove that, okay, if you have eta bar, which has the same quantifier free type as nu bar, then if you replace eta bar, so let's say eta bar is equal to eta I less than k, or not k, let's say L, then you get some eta bar prime, which is eta I concatenated with 0 to the j, as I ranges over L and j ranges on over k, and I replace the etas with the eta tilde, and likewise I have nu prime defined similarly. And what I need to show is that eta bar has the same quantifier free type as nu bar, if and only if eta bar prime has the same quantifier free type as nu bar prime. Because what did I do? I replaced each A sub eta with B sub eta. But what was B sub eta? B sub eta was this tuple here, which consisted of these things. So I know that like if I just look at these indices, and I go from, say, an L tuple of indices to an L times K tuple of indices. Now I just need to check that the L times K tuple of indices has the same type as the other L times K tuple of indices. And okay, that's a horrible check. So I'll do some show and tell very quickly. So here now we're in Google Chrome. Now, elongation was introduced in the following paper. So it's called On Model-Theoretic Tree Properties. And I'm noticing now that we didn't define it correctly exactly. So elongating shows up here. And it's one of a whole bunch of properties. And okay, you have to check that indiscernibility of different kinds is preserved. So how do you do that? Well, you have to play these games where you have to show that, okay, if I replace these tuples with these tuples, then the quantifier free types are still the same. And there's an appendix in this paper where we check these things. And I'll show you just what the proofs look like. You sort of have this endless string of cases where you have to check that all of the quantifier free types align in the ways that they do, writing these very long tuples going on for pages. And so I encourage you to sort of play with it until you believe that it's true, and then believe it, because it's extremely not fun to write such a proof. And I think it would be extremely unenlightening to do it here. Okay, but does everyone have the picture in mind of what elongation does? That you take the tree and you replace each node with this block of length k, where you add a bunch of zeros. So new nodes look like eta tilde concatenated with 0, dot, 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 eta tilde concatenated with 0 to the k minus 1. Okay, so now we're going to put these to work. But before we can do that, we have to define the properties that are of interest to us, which are the model-theoretic tree properties. So here are the basic model-theoretic tree properties. Okay, so we'll start with the tree property. So phi xy has ktp for k less than omega. So this is the k tree property. If there exists some collection of tuples, a eta in omega to the less than omega, such that two things happen. So the first one is paths are consistent. So this just says, whenever I take some eta in omega to the omega, so now I'm not looking at finite strings of natural numbers, but rather an infinite string of natural numbers. Then I can look at each one of its initial segments, and that gives me some index in omega to the less than omega, which corresponds to some tuple in my collection of sequences. So if I start plugging those tuples into my formula, so if I look at phi x eta restricted to I less than omega, I want this to be consistent. And then two, the second example is, or the second condition is that for every eta in omega to the less than omega, so now I'm taking a node in the tree, I can look at the children of immediate descendants, or sorry, I can look at the family of immediate children, I less than omega, and this should be k inconsistent. Okay, Okay, so let's draw a picture of what this looks like. Let me get that here so you can look at the definition while I do it. Okay, so now we have some space. Okay, so here we've got a tree. Now, first things first, let's take a path through the tree. So I take some path here. So what does this look like? Let's call this eta. So here at the bottom, we have eta restricted to 0, and then eta restricted to 1, and then eta restricted to 2, and eta restricted to 3, and so on and so forth. And each one of these indexes some tuple. So I can plug in a restricted to 0 as a parameter into my formula, and then a restricted to 1 as a parameter into my formula, and a restricted to 2 as a parameter in my formula. And that is going to give me a consistent partial type according to 1. So that's why it's green, because you get to go. You get to find the realization. However, suppose I fix some other node like new, and I look at the family of its immediate descendants. So that's some infinite collection of tuples, all of the form new concatenated with I for some I. And as I vary I can plug those into my formula. I have like new concatenated with 0, new concatenated with 1, new concatenated with 2. And that's an infinite collection of formulas. What I'm asking is that that's k inconsistent, meaning that if I take any k of them, the k of them together are inconsistent. Okay, so that's the tree property. So let's consider an example, because this actually, I mean, it looks very esoteric. It's like some kind of crazy configuration, but actually it appears all the time. So let's consider an example, which is the following. So just take q less than. All right, so we have the rationals here, and let's make each node in our tree, a eta, will be equal to some b eta c eta. So it's going to be a pair of numbers, pair of rationals. So we'll start with b empty set, c empty set, way out here. And then we'll break it up into a bunch of smaller intervals. So here we'll have like b0, c0, b1, c1, b2, c2. And then each one of these intervals can be further broken up, like b1, 0, c1, 0, b 1, 1, c1, 1. I think that's right. So what am I doing? As I move farther into my tree, I'm getting a nested sequence of intervals. So I should have said what the formula is. So let's say the formula phi x y z will just say y is less than x is less than z. So it identifies x as an element of the interval defined by the parameters. So what is phi x b0 c0 say? It says that I'm in the interval between b0 and c0. What does phi x b0 c0 say? It says I'm in the interval defined by b0 c0. So if I take a collection of tuples which are indexed by a path, then what I'm doing is I'm taking a smaller and smaller collection of nested intervals. And okay, maybe there's not a rational number that satisfies that, but in an elementary extension, I can always find an element that realizes that, because it's consistent to be in a nested sequence of intervals, certainly by compactness. However, if I take two incomparable things, so for example, what if I say x is between b1 and c1, and x is between b2 and c2? Well, that's inconsistent because I chose them to be disjoint intervals. So inside the dense linear order, I can find a tree indexed by omega to the less than omega, telling me where I sit relative to these intervals, and that gives me an instance of the tree property. It's a nice exercise. I'll just say exercise. if you want to challenge, okay, it's not that hard, is that if you have the strict order property, then that implies that you have 2 TP. Okay, so, and it's really just the proof that we just gave. So if you have a partial order with infinite chains, then you can sort of replicate this argument on a correctly chosen indiscernible sequence and copy the same argument. So if you have the strict order property, then you have a partial order around, and the partial order works just like the dense linear order on a certain collection of tuples. So you can make it work. So to continue the definition, you say that phi xy has the tree property if it has KTP for some k, and T is simple if no formula has the tree property modulo T. Okay, so the absence of the tree property is what it means to be simple. And that defines an important model-theoretic dividing line. All right, now we'll define 2 more. So here's a new definition. So phi xy has the tree property of the first kind if there exists a eta in omega to less than omega such that 2 things happen. So again, paths are consistent. So this says exactly what it said before. If I take a path through the tree and I instantiate my formula with tuples indexed by that path, this gives me a consistent partial type. And 2, now our inconsistency condition is strengthened. So before we said that 2 things are incomparable if they're children of a common node, or I mean, 2 things are going to be k, or okay. We said that k things are going to be inconsistent if they're among the family of descendants of a common node. They're the immediate children of a common node. Now we're going to say if eta and nu are nodes in the tree, and eta is incomparable to nu, then they're inconsistent. Okay, so let's go back and think about our tree. So again, we know that paths are consistent. That's just like before. Now, in the definition of, in the definition of the tree property, okay, in the definition of the tree property, we knew that, for example, these nodes that I've written in red will be k inconsistent. But we were agnostic about what happened between a node here and like a node here. So these nodes just aren't immediate descendants of a common node. They're not of the form nu concatenated with I for a common nu. And so the tree property didn't say anything. I mean, maybe they're consistent, maybe they're inconsistent. So essentially, what happens is to get the definition of the tree property of the first kind from the definition of the tree property, you say everything in the definition of the tree property, which is not forced to be consistent, is inconsistent. So notice that if you have the tree property of the first kind, then in particular you have 2 TP. That formula has 2 TP because descendants of a common node are now pairwise incomparable and so inconsistent. But it says something much stronger also. It says that, if I take two incomparable nodes from maybe far-flung places in different places in the tree, those are going to be inconsistent as well. Okay, so notice that DLO that we had before had this property. So this has TP1. Why? Well, because if you take two incomparable nodes, then what had to happen was they branched at some, look at the meat of these two incomparable nodes, and then at the next stage you had two disjoint intervals, right? Now if you're in a subinterval of this interval and you're in this interval somewhere, then of course these are inconsistent, right? Because I mean they were inconsistent already here, and you know that you're contained in these subintervals, so of course these intervals stay disjoint as you get smaller and smaller and smaller within. So that was actually an instance of this stronger property, TP1. So now we're going to look at somehow the opposite extreme, which is what happens when you take the definition of the tree property and you make everything that's not forced to be inconsistent consistent. So this will be the last thing we do today, and then we'll actually do the theorem next time. So definition, T has, or let's say phi xy has, we'll say KTP2, which is the tree property of the second kind. If there exists, and what's funny is that we're not going to index this by a tree, but rather by an array. So you have AI comma j such that two things happen. So one says for all functions f, which goes from omega to the omega, or omega to omega, phi x ai f of I less than omega is consistent. And two, if I fix a row in my array, and I look just at instances of the formula on that row, as j varies, this is k inconsistent. So let's draw a picture. So you have this omega by omega array. And okay, let's look at this first condition. This says for all f from omega to omega, this thing is consistent. What is this saying? Well, I'm thinking about this function f as telling me which element to pick out of each row. So at the row I, which element do I pick? I pick f of I. So this represents a choice from each row of some element. Sorry, from each row. So it's like snaking through the tree. So I think about this sequence is like a bar I, which is a I j as j varies. And this node here would be like a I f of I. So f of I is telling me which to pick out of each row. So think of this like a path. I'm taking some path in my array where I'm choosing an element out of each row, and then I'm plugging those into my formula. That's consistent. However, if I fix a row, here, and I plug the instances from this row into my formula, that's going to be a k inconsistent collection of formulas. Okay, so what happened to the tree? Well, like I said, one way of thinking about what happened to get the tree property of the second kind is you take the definition of the tree property, and you take everything that's not forced to be inconsistent to be consistent. Okay, but if you do that, then you don't really see the tree. It doesn't actually matter where you are in the tree partial order, because in fact, lots of things that are not related in the tree partial order are consistent. So in fact, you might as well have defined it on an array. So that's sort of the reason why. But you could equivalently have defined it that you have a a tree, and any way of picking things outside the configuration of children of an immediate, of a common node, you get something consistent. That would be equivalent, but this is like the simpler way of seeing it. So if you index the elements in this array by a tree, then you see very simply that it has the tree property. So I encourage you to think about it, but both TP1 and TP2 imply the tree property. And what we'll see next time is that the tree property implies the disjunction of these two. So it says that you can sort of take a witness to the tree property and force it to be extremal. So everything that's not forced to be consistent can be made inconsistent, or everything that's not forced to be inconsistent can be made consistent. These are the two possibilities. So it says that everything sort of breaks to an extreme, and this is an analog of this theorem we had before, that if you're not stable, then either you have the strict order property or the independence property. So you can force it to be either very rigid or very random. Okay, so my plan for next time is to discuss an example where you have the tree property of the second kind. It's a little harder to come up with a natural one. And then we will prove the theorem, the dichotomy theorem. That'll be it for the week. And then we will start talking about the theories without the tree property, which are the simple theories. There's like a nice structure theory for that. And then we'll be doing a little bit more conceptual model theory. I mean, we'll be talking about independence relations and forking and that kind of stuff. All right, are there any questions? No?